All right. Just before I start, I wanted to ask you guys a favor. If you could look around at the people around you, and if anyone is asleep, maybe give them a friendly poke, and you know, and if you could just kind of visualize having a cup of coffee. The brain is a powerful thing. So if you just imagine that you already had a cup of coffee and the coffee break isn't after this talk. Right? Thank you. So I work full-time on the Akka team at Lightbend. We're 5-6 people doing that, which kind of covers Akka HTTP, the Cassandra, Akka Persistence Journal, some commercial parts as well, dealing with the community, working the issue tracker at GitHub, all those kinds of things. I also co-organize Stockholm Scala user group. And yeah, that's about it. So I'm kind of guessing that you have heard about Akka before. Is there anyone who has never heard about Akka? Okay, is there anyone who has never kind of tried out Akka? There's 2 people, 3 people, okay. Is there anyone who is building systems and running Akka in production? Oh, wow. That is really cool. All right, good. So Akka is a toolkit to build concurrent and distributed systems and to kind of try to make that more approachable than kind of the previous state of the art. Using threading primitives, for example, you solve maybe the concurrency problem, but you can never use those really for a distributed setting. And Akka provides tools for both those things. And I would say maybe the distributed part is the absolutely most interesting, even if though the concurrency part is interesting as well. So in the toolkit, there's a bunch of things. We're not going to look at all of them quite yet. So what this Akka typed stuff is about is that we have introduced typed interfaces APIs in actors, which then also gives us the same typed stuff in the clustering stuff, in the distributed systems part, and also in the persistence part, since also all those 3 modules of Akka is about actors. So Akka Streams and Akka HTTP and Alpaca, which is like a modern camel thing based on Akka Streams. They already were typed from day one, all the way through, so those are kind of not covered. And all of these modules have full Java APIs as well. You might not care super much since you're at the Scala conference, but what you may care about is that it gives us strength in numbers with our users. So I would say maybe half of our users are on the Java side. Many users means a more healthy ecosystem and more kind of a bigger push forward. And it also means that, I mean, I'm not sure you can quote me on this one, but I think that Akka is like a gateway drug to Scala. So you might be into Scala in your spare time, but your employer don't allow you to do that. But then you might be able to sneak in Akka, and there will be a shorter step to start introducing Scala as well. I have seen this in a few places at least. So, at the core, the problem we're trying to solve is that we're not getting this free lunch thing anymore. The CPUs aren't getting faster and faster, so we can't write shitty programs. Then a year later is pretty good programs because we got a gigahertz more faster processors. So instead of getting faster and faster processor from that sense, we are getting more cores, maybe even more cores at lower megahertz, right? So we're not going to be able to write single-threaded programs, and those will, we can make Office 95, and then in 1996 it will be fast enough because the CPUs caught up with it. We'll have to write systems in a different way, and maybe even so that we actually need to distribute this processing across many machines, right? So we're building stuff for web scale because we're Uber, or I don't know, Twitter. And we need to do stuff that just can't fit in a single server, right? So kind of the fundamental thing with Akka is the actor model. This is where Akka has its roots. When it was started in like 2008 or 9, it was purely about actors, right? That was the abstraction. An actor was kind of defined in a research paper in the 70s, I think. And like the first kind of commercial implementation that got widespread is Erlang, you might have heard about. And the whole idea with this concept, actors, is that the only way to communicate with other things is through immutable messages. And you do this by putting those immutable messages in an inbox, some kind. And then something makes sure that this entity gets to process these messages one at a time, right? So your actual logic can be written as though you are writing something that is single-threaded. You don't have to think about threading primitives. You don't have to do any locking, synchronization, anything like that. And when an actor sees a message, it can do 3 things. The first one is to mutate its own state. So let's say it has a counter, it can increase the counter, or it can also, in the case of Akka, spawn children. So it can create other actors that will live behind it in kind of a tree structure. The other thing, the second thing it can do is to send messages to other actors. And the third thing is to change its behavior so that when it gets the next message, it will deal with that in a different way. You could argue that mutating the state is also sort of changing how you will behave for the next message, right? But it can actually have a totally different kind of set of messages that it accepts or things like that. And this is basically the whole kind of idea behind it. It's quite simple. So let's get a bit more kind of concrete. I'll start with like just showing off the untyped, the old Akka APIs to have like a reference point in case you're not kind of freshly haven't used them recently. So to write an actor with untyped, you create a class that extends the trait actor, and you implement the receive methods to provide something that will accept any kind of message and do side effects, right? Because all of these 3 things that an actor can do are basically side effects. They're not something that you return. And then from the outside, other actors or code from the outside of the actor system will interact through this actor ref, right? And the only thing you can do through the actor ref is send a message. So this is what it kind of ensures that you're not kind of sticking your fingers on the insides of the actor and touching stuff that you shouldn't be touching. So for a more complete example, I'm going to do Hello World with the old style actor. So we extend the trait and we implement receive for a single kind of message. And we just print the standard out when we get this message. And then we create an actor system. So actors, they always live inside of this actor system, which is kind of the runtime container thingy. So it maintains the threads and the hierarchy and makes sure that the actors get to execute on the thread pools. So we spawn an actor. And what actually happens is that it is put into this hierarchy. So there's like a hidden actor called the user guardian, which will be its parent when we start it like this. And then we send a message to it, or a few, right? And what we may do, this is kind of the main concern from people who haven't really been using Akka much, is that they will do the third message here, right? They will be sending something to an actor which the actor doesn't know about. So in this case, the string, it will just be, no one will know unless you do specific things to notice when there are messages sent to an actor that it doesn't handle, right? So running this, we would get this output, basically. And we can see here that we get no oops printed because it would have to be wrapped in a hello message. So on the typed side, the core thing isn't subclassing actor anymore. It is providing a behavior which has a type parameter which describes what kind of message it will accept. When a message arrives, it has a function or a method that will accept the message and return a new behavior. So this allows us to do the same kind of thing as with the untyped actors. So that is, we can return a new behavior that is a different behavior from before. Or we can return the same behavior but have a state that we actually mutate inside of it. So it provides for both kind of functional programming style and OO imperative kind of programming. If you have reasons to do that, or if you just have a team that are more comfortable with not going down the more FP route. And from the outside, you will still have an actor-ref, but the typed actor-ref has a type parameter which specifies what kind of message you can send to the actor. All right, so the same sample, we define a protocol, a message that we will accept, just like in the untyped example. And then we use a factory from this behaviors namespace object called receive message. And we hand it a partial function in this case, but it actually takes a complete function. So we would get an error actually if we sent it something that matches the type but isn't covered by our partial function in this case. So we match on the case class and we extract the string, and then we return like a placeholder thingy saying we want this behavior to stay the same, right? So we have the message to a new behavior. And this new behavior can also be one of a few different kind of constants that says, don't change behavior, keep running. When the next message comes, use this same function to deal with it. When we start the actor system, the typed actor system, we have to provide like the root actor. So this is also different from the untyped actor system. There is no kind of magical user guardian actor, but instead we provide the root. So in this case, the hierarchy is like flat from the beginning. You could call it flat maybe. And we hand the actor system apply method a behavior that is typed. And that means that the actor system will be typed with the same protocol or the same message. So when we create the actor system with hello in this case, we get an actor system that accepts hello. And in fact, the actor system is also an actor ref to this root actor. So this is something I've seen confuse a few people who comes from the untyped world. So this means that if you're doing something more complicated than a hello world, which is kind of likely, because if you're doing hello world, you could just call println directly. Then you would likely create a root actor that does bootstrapping, that starts other actors, that start other kind of subsystems of your actor-based application. All right, and then we send it a few messages, just like the old API. And we get some output. If we would put the wrong thing here, so I would say like if you are actually using Akka, what you may have seen is the second line here, where you kind of accidentally send the companion object of a case class to an actor, right? Because sometimes it's easy to do that, and you won't get any warning about that, and you don't understand what happened. So in this case, we'll get a compile error because neither of these are an instance of hello. Okay, quite simple, straightforward, I hope. So let's complicate things. This was all kind of stateless actors and kind of useless because the whole point of actors, I would say, is about state. If you have something stateless and you just want to make it asynchronous, then maybe just use futures. So we define a protocol, and I'm going to add another message here to have some state to kind of show off. So we introduce like a sealed trait, a super type that says this is the commands that this actor will accept. And then we add, except for the, in addition to the hello world kind of hello message, we also have a change greeting message. So we can change what greeting that the actor will print when it gets a hello message. Right? And then we define like a factory for our starting behavior, where we take like the initial greeting as a parameter, right? And so we accept the hello message, and we take this greeting from the parameter, and then we take the who from the message, print that, and then we stay with the same behavior. When we get the other message that our actor can accept, change greeting, then we're going to call the factory again, but with this new greeting, right? So we're actually returning a new behavior where we have captured the greeting message from the parameter of the function that we call. So it kind of looks like recursion, but it's not, because we're receiving a message, changing, calling a method, returning something, and it won't be spinning like a recursive function would, but it's rather providing something for the actor system to kind of deal with the next message that comes in with. Yeah, and then we just send it a few messages and get some kind of reasonable output. All right, but I mentioned that maybe you don't like this kind of functional style, or maybe you have some performance requirements that make it too costly to allocate a new behavior for every message that you process. So you want to change state, but you don't want to allocate the new behavior and garbage collect the old one, right? So this is one of the nifty aspects of the API, that it allows both the functional style and the imperative kind of OO style. So to do that, so this is again the same application, but implemented in a different way. We extend extensible behavior, and we provide a type parameter that specifies what kind of message this behavior will accept. And then that extensible behavior is a trait, so you will have to implement two methods. One is the receive method, which is kind of like the old untyped one, but typed. And then we have receive signal, which is for like pre-start, post-stop, things like that aren't really part of the messages of the actor. So in this case, we can just keep a local variable, mutate that, and keep the same instance. Never allocate a new actual behavior. Okay. So we've seen that pretty much all of these except for this last one, I've been using this behaviors.something. And there's a bunch of more kind of factories on there. So like one quite important is behaviors.setup. And what it allows for is to do stuff when the actor starts, right? So not reacting to a message, but instead reacting to startup. And at startup, the only thing you have is this actor context thing, right? So in this case, I am just using it to be able to reach into the actor system and use the logger of the actor system to log something on the actor start. And then I'm returning the actual behavior that is going to run, right? So with this, I will be able to load some initial resources, set some stuff up that I can close over with the actual behavior. So I would return an actual behaviors.receive message and do stuff. Can actually also do mutable stuff inside of that scope. Another nice one is timers. So with timers, it allows you to schedule messages to the actor itself or to other actors. Am I lying? Sorry, schedule messages to itself. So you can fire off like a timeout kind of message that will happen 5 seconds into the future, but only once. Or you can have something that repeatedly sends a message to the actor itself. And you can also use this timers object to cancel timers that you have created before. A bunch more I don't have samples for here, but oh, excuse me. Behaviors.empty is a behavior that can't handle any message, so it would return behaviors.unhandled for every message. So that is not a failure, but it's also not something I dealt with. Behaviors ignore, it will kind of accept any message and say like, fine, I don't care, stays same behavior. So this will be like complete behaviors where you, for example, you have an actor that does something up to a point and then want to switch into not doing anything. Or just in a sample where you need to fulfill the signature. Behaviors.with MDC allows for map diagnostic context. So that is like putting some tags that will end up in all log entries while processing messages. So there you have like a static MDC where you can say like when I create the actor, log entries will always have this map of MDC values in the log entries. And then you also have like a function that goes from message to MDC for that message. So you can actually like decorate the behavior someone else wrote that does logging with introducing like a transaction ID, for example, based on the message that comes in. So the actual actor logic wouldn't have to know about this. It just uses the actor, the context.logging that I showed before, and it will get these MDC values from being decorated with this. Monitor and intercept, those are like also decorating things. Monitor will, for every message that it gets, it will also fire that message off to another actor that you provided, right? That can accept the same kind of messages. So it's useful in tests, for example. Intercept is something that is not quite in there yet. Like we have had different solutions for the same problem, but this is when you want to put something around the behavior that could potentially change the type of the incoming message to another one and pass it to the inner one, or change the behavior that is returned, right? So this is the same, all these built-in decorators like the with MDC, with timers, those are typical versions of behaviors that wrap the actual behavior and does some transformation of the message or the response or the return. Receive partial is more like the untyped receive. So it will take a partial function, and any message that isn't matched, it just automatically marks it as unhandled rather than seeing it as a complete function and throwing an exception, a match error when you don't match all the messages. Receive signal for composing and just doing stuff for the pre-restart, post-stop, and terminated when you're watching another actor. Oh, I'm losing my voice, sorry. Supervise, the whole concept of supervision kind of changes. So in Akka untyped, all kinds of failures, they will bubble up to the parent. In Akka typed, the default behavior is to deal with the exceptions in the actor itself. And if you do nothing, an exception, a failure, will cause the actor to stop. So if you don't want that, you have to explicitly wrap your behavior with this behaviors.supervise and say like, for a runtime exception, restart the actor or resume, or just like the old strategies. But there is no kind of bubbling up to the parent. Okay, let's make a more realistic example. So we're gonna build our own burglar alarm. And I have to cover also a distributed version now in 20 minutes, so I'm going to kind of speed up. So our requirements list is that we can disable the alarm with a pin code, or else the burglar could just turn the alarm off. It will accept notification about activity from some form of sensor. And if the alarm is enabled when it sees activity, it will make noise, call the police, I don't know. So the protocol will be like this. We have the enable alarm. Maybe you should take a pin code as well, because maybe your kids would like turn on the alarm when you don't want it. But for now, we're just going to have a big green button that says, or red, that says enable alarm. And then we have disable alarm, where you obviously really need the pin code, or else. And then we have activity seen, which is this kind of sensor message. So the sensor tells us, I saw the door got opened. And then we define like the disabled state of the actor. And just like the one with the changing state before, the greeting that we could change, we take the pin code as a parameter. I'm not going to change it in this sample, but just to show you how we can pass state along. If we get a message, an enable alarm message, we will switch to the enable alarm by calling the enable alarm method, which I'm going to show you in the next slide. For any other message, we just say like, I didn't handle that. It's not a failure, I just, for example, disable an already disabled alarm. That's weird, but we don't need to make a fuss about it. And if we see activity, that's also fine, right? So for the enabled alarm, still keeping the pin code as a parameter to it. So we close over this parameter. Here I'm using a different factory. So instead of receive message, I'm doing receive. And this one takes the actor context and the message. So every time it's called, I will get both the context and the message. And context provides us with stuff to spawn children, use the logger, reach into the actor system, use the configuration, whatever. When we see activity, we log a warning. Someone is doing something. And when someone disables the alarm with the right pin code, I'm not sure if the backticks show, but we're matching on equals on the pin code parameter here. We're not capturing the pin code. We log an info line, and then we switch over to disabled alarm, right? And we pass along the actual pin code. If someone tries to disable the alarm, but it wasn't the actual pin code, then we also sound the alarm, right? And if someone tries to enable the alarm, when it's already enabled, that's fine. And then we spawn it, and just as I said before, this actual alarm in this case is going to be the root actor of the actor system. So we're passing this enabled behavior to the actor system constructor factory thingy. And then we send it a few messages, and we see that the logs are kind of what we expect. Okay, so in reality, I kind of mentioned this already, but people who haven't used Akka, their kind of main concern, and I would say I especially see this from Java people, maybe not so much Scala people, but also a bit in the Scala community. It's like, I need to unit, this is crazy, I'm going to send the wrong stuff around all the time, right? So after working with Akka-related stuff like the last 10 years or so, this has happened, like I can count it on one hand the number of times. So the actual kind of value in this, I would argue, feel free to have a different opinion, if you still want to go like, that is discoverability. So you come to a new place, you're a consultant, let's say you're a consultant, you have a nice tie and shirt and everything, and you come to a new place and you have to fix their stuff that they totally made it not work. And you dig into the code base, and with untyped actors, it's so much harder to figure out how the things are related to each other. While with typed, you will have the message types to follow all along everywhere, right? Even though this has gotten better with the kind of latest few IntelliJ releases where they have kind of received pattern matching search and stuff like that. Sorry. So even though it gives us kind of other nice things, I would argue that that is kind of the main thing, figuring out how a system is interconnected, which actors speak to which other actors and things like that. So I think this is maybe a general truth, but types helps productivity. That's why I'm into typed languages. So more problems that I see right away when I write the wrong stuff, and less problems in production at 5 o'clock in the morning. A consequence of making everything typed is that in the untyped actors, we had this magic thing, which is the sender. So whenever an actor received a message, we would be able to reply back to it, right? If it was an actor, could just say like, here you go, here's the result. We can't do that in Akka typed. Any clues why? I'm giving away a free Akka license, if anyone can answer this correctly. Yeah, it has to do with the type, so let's look at that. So we have an actor A and an actor B, without letters on the slide I see, but we're sending a request for something to actor B, and that message is part of the protocol, part of the messages that actor B accepts, obviously. But then that actor wants to respond, right? And what it responds with will be like a message from the protocol of that actor. And our actor has its own protocol. So something like this. Can you see like an obvious mismatch here? Like, why would a message from another actor's protocol be part of my actor's protocol? That would be kind of weird, right? Would I have to go, so I'm using this actor that someone else wrote, I would have to go into their code and that protocol and change their message to also extend from my protocol, right? It doesn't make sense at all. So there's no way for us to know on the receiving side what type the sender would accept, right? And this other part, right? So we can't really expect the response to always be in our own protocol. So we need something in between somehow that will accept this response from the other actor and transform it into a message that we can accept. So some kind of transformation function. And from this transformation function, we need to get an actor ref that has the right type parameter. So we can pass it over to the other actor in the message. So you will always have to encode any kind of messages where you expect a response. You will have to put a reply to actor ref inside of the message. So this is kind of a huge difference from Akka typed. Okay, but of course that is something we can solve. So there's like two aspects of it. There are two ways. The first one is when we have just a request-response interaction. So you have seen ask in untyped Akka. And we have an ask here as well that does the same thing. And the other one is when we don't want to have a single request response, but maybe we are subscribing to something, so we get many responses. Or we just want the other actor to be able to send us messages at any point in time, right? So then we will need to use something called an adapter. So ask will look like this. From the actor context, we have a method called ask, which we can pass the other actor to as the first parameter. And then we pass it a function that creates the actual message, right? Because ask will provide the actor ref of the right type. So in this case, to make it really kind of obvious what's going on, I'm passing request for b.apply, right? Which will make it into a function that we're passing in. But you could actually skip the apply part and just have the case class name, which is kind of the normal way to do it. And then the third parameter list of ask is the transformation of the response. So we will have to transform a try of the response into something that our actor will accept, a message inside of our actor. So in this case, we have the protocol of our actor, and we have some kind of an internal got result, got no result messages, which we transform a successful response, or when timeout hits, which that's basically the only way we can get the failure, we transform that also into a message to our own actor. Okay, so this is for a single send a message, get a response. For the other case, we have this context.message adapter, which we just give the transformer and we get a actor ref back with this right type, and we can pass that adapter around to other actors. Okay, 10 minutes to do distributed systems. Skip. A really complicated thing with distributed systems is partial failure. And that is that you cannot really know the difference between if your request got lost, if the other node got the message but had problems. Did it maybe even complete computing the thing, but then it crashed? Or did it partially complete the request and crashed? Or if it was just that someone, clumsy guy with the big scissor in the server hall, cut the cable before the response could get back, right? So the response message could also get lost. And as a sender of something that you need to get done, like a request response thing, you cannot know the difference between these three kinds of failure. So I would say this is like the motivation why Akka works really well for this problem, because we're already dealing with messages, right? So it's easy to model a kind of thing where we have to retry until we get a response back. And for cases where we don't care, we can just do a fire and forget. And maybe that got lost, maybe it didn't, but right, we can decide on the level of guarantees or promise about delivery that we want. Why do distributed systems if it's complicated? You have something that doesn't fit in a single machine. You have something that usually fits in a single machine, but then you have Black Friday and you have to scale it out to 100 for, one afternoon, and then you can go back to one machine. And you don't want to pay for 100 machines for the rest of the year. Resilience, like it's really critical that no user will ever get no response at all. So when one server burns, you will want to have two other servers that can take over the work, right? And then you can add a new third server and be back on track without having any downtime. So what we have seen so far is like actors sending messages inside of one actor system. But it's essentially the exact same thing when you distribute it. So you will have an actor system on different nodes in different JVMs. I think the big difference is, of course, like latencies, how likely it is that stuff get lost, which is basically zero inside of an actor system, and much, much higher. And especially much, much higher if you're in some kind of cloud environment. And then you have serialization, right? So you need to be able to turn your messages into bytes for the wire, and then back again into a message. And that is something that you don't have to do at all when you're running inside a single actor system. Then everything is just memory references. Akka cluster and Akka typed, the core thing is something called a typed receptionist. And the receptionist is something that runs on every node in the cluster. And you can subscribe to this receptionist for a specific key, and the key identifies a typed protocol, kind of messages that someone will fulfill. So you don't have to know where in the cluster there is one of those. You subscribe to changes in the set of existing actors that says that they can provide this message or accept this message. And then when you're building an actor that's going to provide this kind of logic, it will use a register message to the receptionist and register itself. And any other node that has subscribed will get a reference to this through this listing message. And then it can use those actor refs that it knows are in the cluster somewhere and send them a message. Right? Of course, there is no guarantee of delivery here either, so maybe that actor was alive when I sent the message, but then it died just after it, for example. Or it died, but the information that it died didn't reach my node yet. So the receptionist is built on top of distributed data. So it's an eventually consistent thing, so it will disseminate across the cluster nodes within some kind of amount of time if an actor unregisters itself or crashes or is removed. So 5 minutes to do an implementation of the distributed burglar alarm. So this is where I'm going to really earn my startup monies, because I mean, who cares about a single node burglar alarm when you can buy a distributed one? So the requirements list is that we can have any number of nodes, so we can scale out, because maybe I'm going to move to a nice castle here in Tuscany, or maybe I need to downsize and live in like the door, the little room under the stairwell in a house in London. Who knows? So a sensor on any of these nodes can report that there was something happening. And the alarm, which may live on a different node, should sound the alarm when it sees some activity. So kind of simple. So it will look something like this, that we have a separate actor that is the sensor actor that will accept a trigger message, and that will try to pass this message on as an alarm message to the actual alarm. So we're basically keeping the protocol, the messages that the alarm accepts from the previous example. And then we define a service key. So the service key, it takes a type parameter that says, like, what kind of message will this things implementing this service accept? And then it takes a string to identify it. So you could basically have any number of different services that will accept the same message, but you can have unique string names for them, right? Because strings are the best thing for unique things. Then on actor startup, like the first thing we do, we use this setup to do something on startup, and that is that we send the register message to this system receptionist, where we pass the key and a reference to ourselves, right? So I can accept messages from any node that are of this type, the activity scene message. So we're not giving access to the full protocol of the alarm, just the activity scene, right? So we can kind of narrow it down like this. And then for the sensor, so we do like a little message setup with one message that is the trigger of the alarm, that the sensor got triggered, and one that is needed to do this kind of adapting a message from a response from some other actor into our own protocol, right? So we have a message called alarms changed, which is a part of our protocol, but we're going to be sent this message in a different form, and we're going to adapt it. So just like the other one, we do some setup, and we create an adapter on the setup, and the adapter turns a listing from the receptionist, so it's a part of the receptionist protocol. It turns it into our own message, this alarms changed message. And then we use that adapter to subscribe to the receptionist. And then we go into the kind of actual behavior of the actor, which looks like this. So we capture like some kind of identifier, the where, and then a state that will be changing over time, and that is the set of alarms that we know of in the cluster. So whenever there's a trigger, we go through all the alarms we know of, and we send them this activity scene with our little identifier, so we can see that it came from this specific sensor. And then we stay with the same behavior. When we get this alarms changed, so this is the adapted message from the receptionist, that the set of actors that provides an alarm, that set changed. So a node went away, got stopped, or a node started an alarm, but it wasn't about the topology of the cluster, but rather, you started an actor somewhere, and it said, I will provide this service. We will get this message. We're just going to log it, and then we're going to again call the factory method that created this one, but with a different set of alarms. So it's like a changing state, but it's not through a var. Okay, and then we put some config in there to enable Artery, which is the kind of the next to be default remoting implementation for Akka that does the network part. We bind it to localhost, and we let the operating system give us a port. And then we turn off some annoying logging stuff. Then we create 3 actor systems, so all in one JVM. Of course, this isn't like how you would do a real system, because then you could just use one actor system. But to show off the cluster, I can do this in one JVM. And then I programmatically form a cluster by taking one of the nodes and saying, like, you're going to join yourself and form a cluster. And the other 2, you're going to join the cluster that the first node created, right? So this is the seed node thing that you might have heard of it or seen in config files, but through code instead. So the first one would be like the seed node, and the other 2 are joining it. And then at some point in time, we're going to send a trigger to the systems that have the sensor, and we're going to see that we get log entries from the alarm actor. Okay, I'm running over time, but let's just complete these last 4 slides. And then you can have coffee. So to summarize, on a message, an actor can change its state or behavior or send a message to another actor. This is maybe now a bit more clearly defined with the message to behavior function that you provide. Types give you better guardrails and make it easier to understand what someone else has built, and maybe also what you yourself built like 2 weeks ago. And we can make use of this exact same abstraction for distributed and local systems. So how ready is it? We haven't frozen the API send. We don't promise binary compatibility or even source compatibility. We expect only minor changes. It has pretty much been the same since mid-spring, when we made a large effort in, I think, maybe February, March sometime. So you can definitely try it out. Not sure if it's quite production ready yet. And of course, as we don't promise binary compatibility, when a new version comes, you might have to adapt some small things, right? The big thing that isn't ready, isn't done API-wise, is the typed persistence parts. So those you have to be aware that they can change coming 1-2 months. All the cluster and cluster tools and all that has APIs that hasn't really changed for a while, so that you can use like cluster singleton sharding, distributed data. And I think we're hoping to kind of freeze the APIs and release the complete thing during this fall. All samples in this talk, you can find them at this link. There's also quite a bit of documentation already on the typed APIs, other Akka stuff. So, questions, if we have time, that is.
Just for one question, if you have any. Otherwise, maybe you should just, okay. This is going to be a long one, I expect.
Hi, thanks for the talk. So what about the system updates? With untyped actor, we relied on the fact that there are unhandled messages when updating the protocol between 2 actors, for example. So you can update one node with a JVM, adding something new, and expecting that nothing crash, even if it doesn't work, for a meanwhile, and then update even the other nodes without having a down of a system and having everything that is working after all.
Yeah.
But this, I don't think, is possible anymore with typed.
So this won't actually really change, because the problem with adding a new kind of message and having rolling upgrades, so you have one node with an old version that doesn't know about that message, that is serialization. It's not about the actor protocol. So the deserializer on the receiving side, it won't know about the type, right? So that is where the error will happen. And that is true for the old serialization as well. So I don't think that would be a problem. I think you can see that as a transient. I'm a bit unsure now. I'm thinking that if you send it an unknown message, yeah, I would have to check that. It could be that it actually crashes and says that, if you're sending me something that you think that I can receive, but I can't, But that wouldn't have changed since untyped in any way. That's the thing, right? That would only change if you updated the serializer to know about this new message, right? And then you restarted the old node with the new serializer, but not an actor that could accept the message, which sounds kind of unlikely, right?
Okay.
So I think I can take maybe more questions in person. So just come up
just
to me.
because I don't want to steal everyone's time for having a short break and pause for next talk. So thank you again, Johan.